So this video is about the concept of projection of a vector onto another vector, and to motivate this we're going to first look at the problem of finding the distance between a point and a line. So here is a line and I've got a point here, and I'd like to find the distance between that point and the line. So if I draw a perpendicular line from the point to the line, then the length of that line segment that joins the line and the point is the distance. Just to give you an example, consider, say we're in R2, I've got this equation for a line and I'm given a point A with coordinates 1, 1, so I've added that to my little diagram here. What's the distance between that line and the point? Okay, so how we're going to do this, so let me redraw this. Here's the line, here's the point. To solve this problem, I'm going to choose any point on the line, maybe B. So B is a point on the line, and that's easy to obtain. For example, here, so a point on the line for my specific example here on the line is so all I need to do is take that equation and assign my favorite value to x and solve for y, or the other way around. Maybe if I assign, you see a value of, if I set y equal to 0, then 2x plus 4 is going to be 0, so that makes x equal to minus 2, right? You can check 2 times minus 2, minus 0 plus 4 is indeed 0. So I'm going to call that point B, so minus 2, 0. And that's 1, 1. So what I'm going to do now is you see what I need is, I need to have a way of being perpendicular to the line. So that's easy. I'm going to choose a vector n that is perpendicular to my line. That's easy to obtain if I just look at the coefficients of x and y. So so in our case here, n would be 2, negative 1. Okay. And what I'm going to do is join B with A to form a vector. And since I want this distance, notice that it corresponds to what we call the projection of the vector BA onto N. So what's the projection? Imagine that there's light coming in here. Okay, this is light. Okay. Imagine that this is a wall. Okay. So I've got a wall here. The projection is just the shadow that this vector, so the projection of BA onto N, okay, is the shadow that this vector makes onto the wall. Okay, you can see that the shadow would be this. So it's going to create a vector that we're going to call the projection. So this vector here in green, that's the projection of vector BA onto vector N. Now that's pretty long to write, so we're going to use the following notation. So for projection, we're just going to write proj, and I'm not making this up, this is quite standard, proj of vector BA, and onto N we're going to put N as a little subscript here. Okay, and ultimately the distance we are looking for and is going to be the length of the vector. What's the length? That's given by the norm of the vector. So the norm of the projection of BA onto N will give me my distance. So that's why it's going to be very important to be able to project a vector onto another vector. So let's move to projections, and we're going to come back and solve that problem once we'll have solved the projection problem. So here's the projection problem. I give you a vector A and a vector U, and what I'd like to calculate is the projection of U onto A. So if you make a right angle here, the projection is this vector here in green. So that's the projection of U onto A. All right. Now, these two vectors, there's an angle between them. Let's call that theta. Okay. And I'm going to look at the case where theta is acute. Okay. This case where theta is an angle between 0 and 90 degrees, or 0 and pi over 2 radians. Here are some interesting facts. So the projection, okay, I need, essentially to define that vector, the projection vector, I need its length and I need its direction. Once I have those two, I can create the vector, because those two quantities completely specify what a vector is. So what's the length? Okay, it has length. Well, let's take a look at this more closely. If I look at this triangle here, it's a right angle triangle, and the projection is the adjacent side to the angle. So adjacent side means, yes, you got it. I need to use the cosine. So what's the length here? Or what's the let's look at the cosine. Cosine is going to be adjacent, the adjacent side over the opposite side, right? Now the not opposite, over the hypotenuse, adjacent over hypotenuse. Now the adjacent side, it has length norm of the projection, so it's the length of the projection. That's what I'm looking for. The hypotenuse is the length of vector U. Okay, so if I solve for my unknown, I'm looking for the length of the projection. If I solve this equation for this, all I need to do is send norm of U on this side. So the length is norm of U cosine theta. Now cosine theta, you'll recall that we found there's an identity, right, that we can use to find a cosine, and it's related to the dot product. You remember that if I do U dot A, it gives me norm of U, norm of A, times the cosine. So if I just want the cosine, I'm going to send those down here. So the cosine is U dot A divided by norm of U, norm of A. And those two just cancel out. So I just get U dot A over norm of A for the length of the projection. Now I need the direction. Well, the projection has the same direction as which vector? Well, as vector A right there. Okay, because they're pointing in the same direction. Same direction as A. Oop. I need to put it on this in black. Here we go. That's A. So I know the direction. I know the length. Now, if I want to create a vector with a given length pointing in the direction of a certain vector, this is something we solved in the previous section. So maybe let's recall this result. Recall given, let's say, a vector A, to find a vector pointing in the direction of A with a length, let's say, of a length k. Okay. Sort of assuming k is a positive number here. Okay. So what do we do? We calculate. What do we do? We calculate. Calculate what? Well, what you do is you take vector A, you make it into a unit vector. Okay, a vector of length 1. And then you multiply that vector of length 1 by k, and here you go. Okay. So how do I create a unit vector pointing in the direction of A? That's easy, right? It's A over its norm. And then I take that vector and I multiply it by k. So, coming back to my example here, okay, what's the projection of u onto A when they make an acute angle? I multiply the length of my vector, that's kind of like my k, right? Okay, times the unit vector A over norm of A, pointing in the same direction as A. And what do I get here? You see, everything's a scalar. This is a scalar, this is a scalar, this is a scalar. So I'm going to regroup them together. This is u dot A over norm of A squared times the vector A. So what I have here is a scalar and times a vector. A scalar times a vector, well, that's a vector, and that's what I'm looking for, right? The projection is indeed a vector. So that's my formula for the projection. Projection is equal to this. Now, remember I've assumed that the angle is acute. Now, I'm not going to redo this, but we can redo this in the case where the angle is obtuse, and it's the exact same formula. So that's the beauty of it. We just need to remember one single formula for both. So I'm not going to go into the details of that. It's relatively simple, but not crucial for us. So what I'd like to do, though, is come back to my original problem, which was to find the distance between this line and 2x minus y plus 4 equals 0 and the point 1, 1. So just gonna example 2x minus y plus 4 equals 0. A is 0.11. Okay, so I've got my line, I've got my point. Remember, we did actually some work. We calculated a point on the line. We did that. We got minus 2, 0. That was done by setting y to 0. Okay. I can easily get a vector n. We did that also, but that's pretty simple, right? It's 2 minus 1. And just look at the coefficients of x and y. So 2 minus 1. So n is my a in the formula, right? I'm projecting u onto A. So and now what I want, so the u in this situation is vector BA. So u is vector BA and A is vector n, okay, in my formula. So what I want to do is I want to calculate this projection, okay, this guy here, projection of BA onto n, and I'm going to take its norm. So let's first take a look at the projection of BA onto n. Well, what is that? According to my formula, it's the dot product of BA and n. So this is also something I may need to calculate. So let's write B here. B is minus 2, 0. I need BA. BA is done by subtracting from A the coordinates of B. So I'm going to get 3, 1. So the projection is going to be 3, 1 dot product with n, 2 minus 1. So that's u dot A over norm of A squared. Norm of A is A is n, right? So I calculate the norm of n. So n is 2 minus 1. And so the norm would be the square root of 2 squared plus minus 1 squared. But when I square everything, the square root disappears. So I just need to take the components of n and square them. That's the norm squared. And finally, I multiply that by a, but my a is n, so what's n again? 2 minus 1, like that. So I need to simplify this here, obviously. So the dot product at the top is 3 times 2, 6, plus 1 times minus 1. So 6 minus 1, 5. And at the bottom, 2 squared is 4, and 1 squared is 1. So 4 plus 1, 5. So it's a coincidence, actually. We get 5 on 5. Normally it's some random number, but here is a nice number. It's going to be 1 times 2 minus 1. So we get 1 times, right, this is 1 times 2 minus 1 is just 2 minus 1. So it actually turns out that the projection of BA onto n is n itself. That's because my diagram over there is not quite accurate. So in fact, if n is 2 minus 1, as BA would be actually perfectly like this, so they form a right angle like this. So anyway, it's just a coincidence. Now to find my distance, I just need to, so the distance will be equal to the norm of this projection vector. So now I take the norm of the vector 2 minus 1. So I get square root of minus 1 squared, square root of 2 squared plus minus 1 squared. Okay, and that gives me square root of 4 plus 1 square root of 5, and that's the distance between the point and the line.